So what is QR decomposition? So you take any matrix A, right? I can think of this as these column vectors, right? A1, A2, etc. An. Well, remember this is not this is true for any matrix, okay? Not necessarily square matrix. You can take fat, tall, whatever, right? So I can write this as what? If I apply Gram-Schmidt's orthogonalization, so what can I do? I'll write A1 as some constant times A1. Why? Because if I'm looking at orthonormal, then I want to normalize A1 to get unit norm, right? So this will be alpha A1. Okay, let me call this as alpha 1, A1. Okay, so let me write it like this. So how do I orthogonalize, right? So this is what I do, right? So how do I do orthogonalization? Let me not even do just let me do orthogonalization, not orthonormalize, right? A1. So what happens to the second one? A2. So how can I write A2? So what is the procedure? You took this, and then how did you get the second one? So it's a linear combination of A1 and A2, right? Do you agree? Or sorry, it's not A1. So let me call this as A1 tilde. Okay. So it's A1 tilde and A2 tilde. Do you agree? So this is alpha. Let me write this as 2, 1, A1 tilde plus alpha 2, 2, A2 tilde, right? This will give me the second vector, which is orthogonal to A1 tilde, right? You understood, right? So A2 tilde, how did we get V2 tilde? V2 tilde is V2 minus projection of V2. So projection is nothing but in terms of V1, right? V1 tilde. V1 tilde is actually some constant times V1, right? So essentially, it's a linear combination of V1 and V2. V3 is a linear combination of V3, V1 tilde, which is V1, and projection of V3, which is V2, right? So on to V2 tilde. So it's a scale version of V2 tilde, which is some linear combination of V2 and V1. Therefore, overall, it is a combination of V1 and V2, right? Is that clear? So this is what we get here, right? So I can write this and so on. What will be the last one? Alpha n1, a1 tilde, and so on. Alpha n, so an tilde or an, right? So this is what we get. Do you agree? The last one is a linear combination of all the previous, right? So that's what we get, right? Is that clear? So what will be the last one? Vn tilde. It's Vn minus something, right? So it will be a linear combination of all Vn's or Vn tilde, whatever you want to call it. So essentially, I can write this matrix as what? So this matrix turned out to be, what is this matrix? So if I look at A times X, right? So if you look at AX, so this is a vector. Do you agree? Matrix times vector is a vector. So if you look at the first entry, what does that correspond to? Or if you look at this whole vector, I can write it as linear combinations of columns of A, right? Do you remember that? So I can write it as linear combinations. So what will be the coefficients? Coefficient will come from X, right? So what do we have here? These are all linear combinations, right? Of some A1 tilde, A2 tilde, and so on. So how do you get this? How do you get this? So it's essentially, I can write a matrix. So basically what happens is, so what do I get here? I get a Q matrix, right? This is your Q matrix. Do you agree? This is your Q matrix. Because they are orthonormal, right? I have orthonormal. How did I get this? Some linear transformation of A, right? What kind of linear transformation? It turns out to be some sort of an upper or lower triangular. Okay, so essentially what it means is that I can write A as Q times R. Okay. So what is this Q matrix? Q matrix is basically, let me write it as this: Q1, Q2, Qn. Of course, whatever we did so far, we just orthogonalized it. You can also orthonormalize it, right? So again, it's basically the effect is multiplying by a constant, right? Normalization. So this has the following property. Okay, so if you look at, for example, Q1 or Qi transpose Qj, that means if you look at the dot product of two columns, right? Inner product of two columns, it will be 0 for all I not equal to j. Okay, you take any two different columns and take the inner product, you will get 0. That means they are orthogonal, right? So of course Qi transpose Qi is what? Is 1 for all I. That means Q1 transpose Q1 is 1 because we have orthonormalized, right? So I can write A as Q times R. What is R? What is R? Hmm? R is a matrix like this. Okay, so it's an upper triangular matrix. It looks like this and a 0 here. Okay, fine. Fine, right? So everyone, is that okay? So why is it useful? So keep this in mind. Even if the procedure is not clear, it's okay. So I can always write, given any matrix A, I can write it as Q times R. Q is an orthonormal matrix, the columns wise, and R is an upper triangle. So why is it useful? So suppose I have an equation Ax equal to B. I can write A as QRX. Remember, which is easy, right? You have to find those coefficients, that's all. So now, what is the inverse of Q? Suppose Q is a square matrix. What is the inverse of Q? Okay, let's look at this. What is Q? This is Q, right? QL. What will be the Q transpose? This is Q, by the way. What will be Q transpose? I have to make the columns rows, right? So I'll have like this. This will be Q1 transpose, right? This will be Q2 transpose, and so on. This will be Qn transpose. What do I get? See, Q1 transpose times Q1 is 1. So I get 1 in the 1, 1 position. What is Q1 transpose times Q2? 0. What is Q1 transpose times Q3? 0, and so on. What is Q2 transpose Q1? 0. What is Q2 transpose Q2? 1. So essentially what you get is an identity matrix, right? So if I pre-multiply this whole equation by Q transpose, that is Q transpose Q or X equal to Q transpose B. See, all that I'm doing is multiplication, okay? So I'm just taking Ax equal to B, multiplying by Q transpose. That means I have to do QR decomposition, multiply. So what can you say about this? This is identity, right? So what we have? We have, I'll call this as B tilde, okay? This is another vector. So what do we get? Rx is B tilde. Fine. What is Rx? It's easy, right? So this is the kind of matrix that we'll have. X1, X2, Xn. This is B1 tilde, B2 tilde, Bn tilde. Now, how do you solve this problem? Well, you should not, we should exactly go in the opposite direction. Let's start with this. There is only one term here, right? When you multiply, so this is entire 0. So when you multiply this, what do you get? This number gets multiplied with xn, right? Okay, so let me call this as Rnn, okay? Because this is the nth entry of R matrix. Times xn is Bn tilde. How easy is that, right? So I know what xn is, right? Bn tilde divided by Rnn. So now what happens to this next row? You have these, the diagonal entry and the off diagonal. It's xn minus 1 comma xn minus 1, right? That's xn minus 1 comma n minus 1. That will be the entry. Sorry, why did I? It's R n minus 1 comma n minus 1, right? It gets multiplied by xn minus 1 and xn minus 1 n gets multiplied by, sorry, why did I say that? This is Rn minus 1 n gets multiplied by xn, right? This gets multiplied by xn minus 1. This gets multiplied by xn, right? That is equal to bn minus 1 tilde. Now, how do you solve this? See, I know xn, right? I'll substitute this here, right? So I'll get a number, right? I know Rn minus 1 comma n, multiply that. So take the entire thing to the other side, divide by this thing. So I'll get xn minus 1. You can recursively do, and it's as simple as that, right? So you don't need to find inverse of a matrix and all that. It's computation wise straightforward, right? Is that fine? That's why QR decomposition pretty easy. Okay, everything is fine. Okay, so okay, so at least we have done one decomposition, right? So which is QR, right? We have not studied any other decompositions, so we will see a few more, maybe at least two more decompositions. Okay, any questions? I'll pause for a minute, and if you have any questions, feel free to ask, and we'll move on. Any questions? The good thing about this is, there is QR decomposition for any matrix you give. Okay, there is no condition on the matrix. Okay, so of course, if you have, let's say, two. Let me ask you this now. Suppose I have A1, A2. Okay, so what is the size of this? N cross 2, n rows and 2 columns. So what do you think will be the QR decomposition? What do you think is a QR decomposition? Huh? See, A1 belongs to Rn, right? So in Rn, I'll have n basis vectors, right? I can have n basis vectors. Do you agree? So first one will be scaled version of A1 itself. Second one will be linear combination of A1 and A2 to get a normalized vector which is orthogonal to normalized A1. What about A3? Well, orthogonal to both but living in R3, right? Or Rn. So I can keep on doing that to get the entire set, right? So I can do, for example, this is Q1, this is Q2. Well, Q1 and Q2 are related to A1 and A2. After that, you just go in the orthogonal space, right? Whichever vector you pick. So you have Qn here. What is the size of this? N cross n. What should I get now? I should get n cross 2. Now what should I multiply here? It's 2 rows and n columns. Do you agree? Or sorry, n rows and 2 columns, right? Do you agree? So that means I should have a very tall matrix, right? Something like this. N rows, 2 columns. Okay. Now what should be the entry here? Well, it should be a lower triangular, right? So what will be the triangle? This is, right? There is a 0 here and there is a 0 here, right? Only these two entries, this will be non-zero, this will be non-zero, and this will be non-zero, right? That's all. Do you agree? Okay. So that's what it turns out to be. Okay. Depending on how you write it, so of course I can also write it as a lower triangular if I take the transpose and so on, but it doesn't matter. So is that clear? So the remaining will be 0 because all the other columns here will get multiplied by 0 and it doesn't matter, right? It will add 0 to the resultant. So that means there is no vector component of A1, A2 lying in that span. So the coefficient should be 0. Okay, is that intuition fine? So how many of you are comfortable with MATLAB? All of you are, okay, those who are comfortable with MATLAB, probably I'll give a few computation like this and, programming assignment. Those who are comfortable with any other language, for example, C, whatever, right? So you can use that, any language that you are comfortable with. Okay, is that fine now? Okay, so now let's move on. So let's look at one more very important notion, which